Hi, and welcome to the last lecture in this semester in the subject Construction of Electronic Systems. And today the lecture will be about thermal management. This is a field which is quite important and getting more and more important lately because the electronics is getting miniaturized, and at the same time the power consumption is increasing per chip, and the chips are get smaller. This means that you get the same or even more power dissipated in the smaller area. And electronics is a field, or in this area of electronics, I would say the highest power densities can be found. And I will show you quickly why. And just one thing before we start. Most of the designers underestimate the cooling of their components, or let's say they underestimate the heating, and then they do not provide adequate cooling, which then results into lower lifetimes of the devices or even premature failures. On the other side, there are areas of the electronics engineering where the cooling of components is of essential importance, such as LED lighting in the car industry or indoor lighting industry, and computer industry as well, and power supplies, where the temperature of their devices is simulated very thoroughly before the device is actually manufactured or even designed the prototype. Before they design the prototype, they already calculate all the relevant parameters regarding the temperature and the cooling of the device, and they take that into account when they design the prototype. And this is a really field which we cannot go into real details in one single lecture, but I would just like to show you a few general physics behind it, and then we will go a little bit into the PCB design, where I will show you a few techniques how to efficiently cool the components. All right, the thermal management. And here is a single graph that shows the temperature and the heat flux density in watts per square centimeter. And here you see the solar heating around 100 milliwatts per square centimeter. Sun radiates the Earth every day. And then the rocket motor case and the re-entry for Earth orbit, the nuclear blasts and stuff that are really, really powerful, but they are comparable to the semiconductor electronics, as you see here. The electronics is miniaturized really, really a lot, and at these small areas you have a lot of power dissipated. For example, a microcontroller can have 100 watts power dissipated at a single square centimeter of the die area, where the laser diodes are the winners, where a few square microns can have a lot of power dissipated. So this is an area of electronics which can be compared to the most powerful things you can imagine ever man-made. And the next slide shows the microprocessor power density, a few tens even watts per square centimeter, which is more than a traditional light bulb or sun. So therefore the power dissipation and the heat dissipation and cooling of the electronics should not be neglected. There are three physical transfer mechanisms: conduction, convection, and radiation, and we will go through each of one of them. First of all, the conduction is, as you all know, the movement of molecules or electrons or atoms even that collide with each other, and that movement then causes the heat transfer through solids, liquids, or gases. The convection is the movement of gases or liquids because of the different densities at different temperatures, and the radiation, according to the Stefan law, it's electromagnetic energy. First, conduction. As I told before, the conduction is a movement of molecules within all three types of the matter. It is best described by a simple linear differential equation founded by Joseph Fourier. It's a Fourier law, which tells you that the heat transfer is proportional to the gradient of the temperature and the area, of course. So if you take that into account, a single parameter is defined for a material which is called specific conduction, sigma Th. And this specific conduction is different for different materials. Well, if you look at the equation here, you see that the power that is transferred through a single piece of material is proportional to the difference in temperature and the heat resistance. And the heat resistance is this parameter here, dependent on the length and the area and the specific conduction. It's very similar to the electrical conduction. So actually we have equivalent electrical model, which models the heat transfer with the same equation as an ohmic law. So this ohmic law tells you that the voltage is proportional to the current and resistance, while here the temperature difference corresponds to voltage and the current corresponds to power and the resistance to the thermal resistance. So this is equivalent thermal electrical model. So we can use electrical circuits to model heat transfer. And about the specific conductivity of materials, you can see that metals have the highest conductivity while gases have the lowest, and liquids and some non-metallic solids are in between. This is because the highly conductive material, electrically conductive material, also have good thermal conductivity because they have a lot of free electrons. So the free electrons are the ones who are conducting heat here. Free. While here in liquids and gases, the molecules are so weakly linked that the movement of these molecules, the thermal motion of these molecules does not spread so quickly. Therefore, liquids and gases are the strongest or the highest insulators, thermal insulators, of course. Now, these are values of different thermal conductivities of different materials, starting with air, giving it a value of 1, and then the ratio towards the air. You see that FR4 and the epoxy resin itself has quite low thermal conductivity, while the copper has very large thermal conductivity. That means that it will be the best thermal conductive material on the PCBs with respect to FR4, which is very low, and the air even lowest. The highest conductivity has a diamond among all materials, and this is because it has very, very stiff crystalline structure. So what is the reason? Well, the diamond is not conductive. It is actually a semiconductor with a very wide band gap. So the electrons do not conduct well, but the stiff crystallographic structure is. Okay, doesn't matter. The diamond will not be used in electronic circuits for good thermal conductivity, of course, but the copper will be. The heat capacity is another parameter which we have to take care, because the piece of material does not heat up instantly. So it needs certain energy to get a certain temperature difference. So this is defined by this energy conservation law. Well, the change of temperature is proportional to the power, the mass, and the heat capacity, the specific heat. How many joules you need to heat up a certain amount of material for a single degree of Celsius or Kelvin even. So the equivalent electrical model for that would be a capacitor, because the change in voltage actually over dt is equal to the current that flows into capacitor divided by the capacitance. So, sorry, du over dt, which means that you can model the heat capacity of material with electric capacitor, and all the units also correspond well. Now, by keeping that in mind, you can model, let's say, a transistor with a certain resistive capacitive circuit. So a transistor, for example, has a silicon die, and this silicon die has some junction on it, and the junction is treated as the source of the power of the heat. Why? Because on the junction, if you imagine a single PN junction, on a PN junction you have, through the PN junction you have current, but on the PN junction itself, here at the vicinity, you have all the voltage. So the current times the voltage is of course the power. So all the electric power is generated at the junction of the component. So that's why we call it junction. Well, it depends of the type of component, of course, but let's say for a single PN junction, that would be the case. And it's still called the junction temperature. So we have a junction temperature somewhere, and then we have a silicon die, and then we have some glue or some epoxy or whatever. Then we have the case of the component, and all that leads to a outside. So here we have the case temperature. We call it case temperature. And then we have ambient temperature somewhere around it. So from this die to the ambient, we have a few resistances. And each of these material with different resistance, thermal resistant properties, it has also different capacitance. So all that is then connected together as a single circuit, transferring electrical power through this, and each of these parts have a certain voltage drop, which is then actually a certain temperature drop in terms of heat or heat transfer. And then we have the junction temperature and we have the ambient temperature, and there is a certain difference between those two. And by using this circuit, we can calculate or simulate even in, let's say, any electrical circuit simulator such as SPICE. We can simulate the junction temperature if we know the power, if we know all these parameters, and if we know the ambient temperature. So these models are very well defined by manufacturers. So for example, this case of this transistor is very well defined, and all these parameters are known, usually if the manufacturer provides them, of course. So if you know the case temperature, then you can calculate the junction temperature if you know the heat transfer power. Now the problem is that usually you don't know the case temperature because you have a lot of other unknown or less well-defined parameters, such as how many copper is here, what is the size of the PCB, what are the components around, how is the PCB oriented, does it have any cooling or extra, let's say, any cooling components on it, any heat sinks, maybe some fans that are blowing air over it, or whatever that you can make to cool your PCB. And all that is very hard to define and very hard to simulate. So for a component, it's quite well defined. And from the junction of component to the case, usually what we can account for is just the conduction. So this is a heat conduction model. There are no other parameters or other physical heat transport mechanisms accounted in this model, only the heat conduction and of course the heat capacity of these different materials. And by using that you can simulate in LT-SPICE, let's say for example, there is a MOSFET here, and the power of this MOSFET is then fed as a current source into this RC circuit. This is the case temperature, and by using simulation you can calculate the junction temperature. And this is how it looks like. The gate voltage, the power is the red curve, and the green is the junction temperature. So here you can see how the junction temperature quickly increases to this value, and then the component cools down, and when the next power spike enters, you have another heating. So by such a simple simulation, you can simulate your component. While the problem here is that what we have to fix here is the case temperature. But we don't know the case temperature usually. As I told you, the case temperature is not fixed. It is a part of the whole PCB. So other heat sources are there, and there is a lot of way to go for the heat from this case to the ambient, which is somewhere in the vicinity. And we don't know well, usually we don't know well these properties, because it depends how we design the PCB. The convection is another physical parameter which is even more important. When you come from the component to the air, to the surrounding, usually a lot of heat is transferred with convection. The problem of convection is that it's a very nonlinear process, which means that you cannot just simply take this equation which I show here, which is just the most simplified equation you can get for the convection, and it almost never work well, because this is a very well simplified equation which simulates the convection as it is, as the conduction, with the same Fourier law, which almost never work. So this convection factor is very dependent on different mechanisms. For example, in a laminar flow it is quite well defined, but in turbulent flow it is totally off. So this convection parameter could be somewhere from this to this value without knowing you well. So you don't know it well. The thing is, the only thing you can see from this chart is that in gases and liquids you have, of course, in liquids you have much higher convection factor than in gases. If it is forced, that means forced with a fan, it's even much higher, but a lot depends on the fan. But the highest convection parameters can be get if you change the state of the material, state of the liquid into gas or back. So boiling or condensation actually has the highest potential of heat transfer. And actually the boiling and condensation is used in so-called heat pipes. This is an example of a heat pipe when you have a pipe, and here you have some liquid, and then when the heat is absorbed, this liquid evaporates and it is transferred to the upper part of this pipe. When the heat is transferred, let's say, into some other liquid that goes hereby, or it is transferred to the air by some cooling with this fan or something similar. When it cools down, it will condensate again, and then it will flow down to this part here when it gets evaporated by this heat again. Well, this approach requires all the time a correct orientation, so that this is bottom on the bottom side and this is on top side. So the gravity works on this liquid to transfer it to the bottom side. Of course, that would be really hard to use if you in the laptops, right, or computers even. So you need something else to transfer the heat to the downside. To transfer the cooled liquid to the bottom side. And in heat pipes in electronics, this is done by this metal braid, because the metal braid here has a capillary suction principle, where the water here, or the liquid, condenses here. It is sucked back to the hot side by capillary suction of this metal braid, and by that the flow is assured. So here the liquid boils, and of course the pressure then presses it to this side there, and here it condenses because you have some big cooling fans here, and then this metal braid is sucking the liquid back to this hot part here. And such a heat pipe has really the best conduction you can get. And such heat pipes are then used in electronics, taking the heat away from the microprocessors to the cooling. So here is the microprocessor, and this takes heat to the cooling fins. And here is probably the graphics card, and again heat is taken to the cooling fin here. And this is in desktop computers. So you can all see how important and how well are these systems designed to take heat away from the microcontroller. So if you have 100 watts per 1 square centimeter here, you certainly need a really good conductor to conduct this heat away. Now, the third principle is the irradiance. As you all know, the Stefan law is describing the irradiance heat transfer. And here, the best thing is that it's very dependent on the temperature. The factor of 4, or sorry, the exponent of 4 makes this irradiance really effective heat transfer at high temperatures. But at temperatures at which the electronics work, that is actually not the case. So here, at lower temperatures, the heat transfer is not that efficient. So irradiance does not effectively transfer the heat with electronics in normal environment, except in space. In space, the heat transfer would be the only heat transfer from the satellites towards the empty space. So, what is the only really hard to define, or let's say quite often undefined parameter in this formula is this efficient or so-called emission coefficient. Emission coefficient is what it actually is dependent on the surface. So the emission coefficient could be almost 0 if you have a highly polished surface, or it could be all close to 1 if you have very matte finish with a special paint. And it could be anywhere in between. So sometimes when you watch electronics with thermal cameras, you can see some of the components that are really cooler than they actually are, or hotter, because your emission coefficient in your thermal camera is set totally wrong. Usually it is set in around this value, around 0.95 or 0.89, somewhere here. And these values are, well, quite often seen in electronic or surfaces of electronic devices because they are covered with some color, like paint or whatever. Well, the thing is that there are many metallic surfaces as well, such as aluminum or copper areas, and there your emission coefficient could be really low. And this means that here you can have wrong reading. We use all that parameters to model temperature in electronic devices, and for radiation and conduction it's not a big issue, but for convection we have to use so-called computational fluid dynamics, CFD, which is actually used for any liquids. They are using this to model wind turbines or water turbines in electric plants. So all that this computational fluid dynamics is used for, and also for heat transfer. And by that you can simulate the natural convection, airflow of the integrated circuits, and the forced convection using cooling fans. Well, all that can be used in electronics, of course, as I already shown in these examples. And in electronic coolings, we also usually have two problems. One is that we underestimate the heating sources, and therefore we do not provide adequate cooling, which then leads to overheating of your components. And the other is that we over-engineer the cooling, which means that we cool too much, more than necessary, and then we have increased weight, size, and cost of your device. All that should be avoided. So we have to first calculate how much power is dissipated at the most critical components. And then we have to know what are the max thermal limitations. What is the maximum junction temperature of component, which actually depended on the component lifetime. So the component lifetime is a function, of temperature mostly. And we say that for each doubling the temperature, the component lifetime decreases by a factor of 2. So if for 25 degrees Celsius we have, I don't know, 100 years, then for 35 we have 50, for 45 we have 25, and so on. For each 10 degrees, I don't know if I said correctly, but for each 10 degrees of Celsius, we get 1/2 of the lifetime. That's a rule of thumb. So that means that if I go even further, you will see 25, let's say, I don't know, 12, 6, 3 years, and 85, year and a half. So that means that we have to take care that the maximum junction temperature is not increased or overseen that by because not only the component will fail, actually the lifetime will be shorter. The second thing is the maximum ambient temperature at which your device will be working at, and that depends whether you use it on the desk in your office, or you use it in your car next to the engine, or maybe you will use it in the I don't know, some hot areas in Dubai, for example. And all that should be taken into account. So that is another very important parameter. And even if you use, let's say, device in your desk, usually in your office, let's say a laptop, for a certain component you have to count the internal temperature of the laptop, not the external one. Because for these components, the first cooling would be from the PCB to the surrounding, which is still inside the laptop, and then cooling towards the air outside of the laptop. And the third thing is the maximum temperature of the housing, because here, of course, it's all usually and also a safety matter. So if you can access the hot parts of your device, you should not get some burns. If you have a power amplifier or a power supply, for example, you have some cooling fins that might be accessed to touch. And of course, you have to take care that do not heat too much. I think usually 60 or 65 degrees is the limit. So you have to take care of that too. So all that are the main limitations which you have to take into account when you are designing your device for cooling. So what we usually have in the PCBs, if we now move to the most, let's say, usual topic of our lectures, of our subject, we have components on PCB. And these components are cooling either through the PCB and through their own housing towards the air, or they are cooling through the heat sinks. The heat sinks are, of course, applied extra to the top or to the case of the components. And the cooling without heat sinks is done primarily through the PCB areas and, of course, directly to the air. And the cooling goes through the pins directly to the air or through the PCB layers. While in the case of heatsink, primary path is usually always taken or considered to be the one through the heatsink. So all the rest are usually much less, I would say, contributing to the cooling. So here the primary cooling is just that one. And here all over the place. Okay, what are the parameters which are usually taken? The first one is so-called RTH junction ambient. So the junction ambient is the thermal resistance between the junction and the ambient of your component. And the power, of course, is transferred from the mid part or the midpoint of your device, of your component from the junction in all direction. But here I just show only one. So what you do, you provide or you apply electrical power to the component, and the heat power is then transferred to the surrounding. Now you have to account here in this parameter all the possible heat transfer paths are accounted, which means if you check the datasheet of your component and you get this value, you have to know that this value is accounting all possible standard heat transfer paths. So that means that that manufacturer has actually to make the measurement on a real PCB with some, some standard designs. So you have to know that this value can change a lot if you design differently. It can be lower or larger or higher. So this value is usually taken as the first approximation for calculating the cooling of your component. Usually it is used directly for cases without heatsinks. So the component housings without heatsinks, it can be used to compare different cases of the same component. So if your component is provided in different case sizes, then you can compare the values of RTH directly and you will get the comparison. And can be used to calculate the junction temperature, but you have to make sure it can be used only if your design is actually the same or similar enough to the test procedure, to the test conditions of the manufacturer. Otherwise, you will get in your design a different value, because this is not a simple single parameter value. As you have seen before, that RTH junction ambient is dependent on everything. So not just a single value. All right. So without heatsink, we take this value as the first approximation, but then we have to add other parameters. As I said, the air of course, the air temperature, yeah, but the PCB transfer, the air movement, whether we have forced air convection or we have natural air convection, the orientation and stuff. So all that is very, very different from case to case. So if we use heatsink, it's a little bit easier, because if you use heatsink, then what you take is the RTH junction case, which means it's not junction ambient, it is junction case. So just between these two parts of your component, which means actually that here this value is very well defined. This value is well defined by who? By manufacturer. And well defined by the manufacturer means that, well, who would know better than manufacturer of the component? Which means you can trust this value. This is trustworthy value. You can trust it. This one, you usually don't use directly for calculations. That one you can trust. But then what you have to add? You have to add the resistance, thermal resistance of the heatsink, of course, and the thermal resistance of the junction of the surface here, this small air gap between the heatsink and the component. And this interface between heatsink and component could be different regarding its roughness, and the air which is kept between these two surfaces could be very bad heat conductor, which means that you can really increase the conductivity of the heat between these two surfaces by adding some extra filling within to get rid of the air. And for that, we have thermal grease. And thermal grease is a much better conductor than air, which can then significantly improve the thermal conductivity here. So here I give you a few typical thermal resistance values for different cases. These are the through-hole cases and these are SMT cases of different sizes. So this is RTH junction case and junction ambient for these cases here. And here are the thermal grease or without thermal grease resistances of these interfaces, thermal resistances of the interfaces if you add thermal grease or if you don't add it. So these are all values you can then choose or take as a orientation values for your designs. For SMT components which are not intended for heatsink, you have to use the junction ambient value, which is this one here. And it all depends on the heat, on the airflow speed. In still air or with some airflow, you can get quite some different values. And as you see, the SMT components could have quite low junction to case resistance, but because the cooling from the component to across the PCB to the surrounding ambient is not that efficient, the values of the junction ambient could be lower. But as I said, all these values really depend on the design. And this is important to remember. These are not constant values. Now, if you added some heatsink, you could get much closer results by using these values and adding the resistance of the heatsink itself. So how to choose a heatsink? First of all, you have to know the thermal properties of your component. For example, this would be a RTH junction case of your component. We add some thermal grease resistance to it, which you also get from the manufacturer, and then you calculate the power dissipation on component. You calculate it from electrical properties. You take some ambient temperature. Let's say this is inside this component is inside a power supply, so it gets very hot inside, and then you take the maximum junction temperature of this component to the desired mean time to failure or lifetime, and then let's say this is 110 degrees for your power supply to last as intended, and then you calculate the heatsink resistance, because how you calculate the heatsink resistance, you take the ohmic law, so the maximum junction temperature, this value, minus the ambient temperature divided by the power which has to be dissipated, which is the same as electrical power, and then you subtract the resistances which are already there, which is the junction case resistance and the thermal grease resistance. So on all that gives you this value here. This is the value your heatsink has to provide. Now, how you choose the heatsink? Well, the heatsink properties are given here for a certain heatsink from this data sheet. So it gives you the thermal resistance at some certain length. So this heatsink, this is a cross section of the heatsink, and then it could be bought at different lengths. So this is the length of the heatsink. If you draw it in 3D, you can imagine now like that. Now, if the heatsink is twice as long, it will not get twice as low thermal resistance. So that's also important to know. So for each heatsink, you have to choose according to the manufacturer's data. And these are, for example, manufacturer data for the heatsink, which tells you that if your temperature difference between the heatsink and the surrounding air is lower, then your heatsink is less efficient, which means you have to add a certain factor to it. So if the manufacturer data are usually given for the temperature differences of 75 degrees. So if surrounding air is at 25 and the heatsink has 100 degrees, then it would have such a heat resistance. But if your heatsink has lower temperature, then the heatsink resistance would be larger. So why is that? Well, the reason is very simple. At a smaller temperature difference, you get less radiation and also less convection. And that's all accounted into a single value. So this value of a heatsink includes all three values, all three mechanisms: the radiation, convection, and conduction. And I must say one thing: the conduction is the least contributing. So the conduction is not contributing a lot to the heatsink properties. As you all know, the air is a very bad thermal conductor. So the main contribution of a heatsink is convection. The convection has the highest contribution to the temperature or to the cooling effect of the heatsink. So this is a correction factor which you have to apply for a heatsink if you have lower temperature difference. Also the length. For example, this is a property of a certain heatsink where at length 3 the nominal value is given. So if you make it twice as long, so twice as big as well, so that would have length 6, you don't get half the thermal resistance. Actually, to get half of the thermal resistance, you need 5 times larger heatsink, because the heatsink, if that's the size of the heatsink, you see, you put your heat source, let's say, in the middle, so it has to conduct towards the edge, and then it would also, of course, cause convection. Now, if you make it 5 times longer and put your heat source in the middle, then it still has to travel all the way to the rest of the heatsink before it gets really well dissipated. So that conduction is also taken into account. Therefore, for twice the effectiveness of the heatsink, you need 5 times larger heatsink. That's just example for one single type of heatsink. Of course, for other types of other sizes, it could be different, but it's not linear. That's what I want to say. And the forced convection. If you use some fans to force the air and to blow the air over a heatsink, then you have to know what is the speed of the air. And usually it is given in a very strange units, which is called linear feet per minute. The units are also cubic centimeters per second. That could be also a possible unit, which would be more reasonable if you ask me. But this could be easily converted by online converters. You can get them if you want. Now, the property of heatsink would give you also this graph if it's a proper heatsink intended for fan. So it will say, okay, at 200 linear feet per minute, you would get thermal resistance of this heatsink 2.6. So this would be then a nice starting point. And you will, if you need another thermal resistance, you may find another fan that blows your air faster. Okay. These are all options you can take, and you can take all that and model your thermal circuit at the end. As you see here, you have the junction temperature, and here you have the ambient temperature, and all that you have in between. You have the junction to case, case to sink, the heat resistance of the heatsink itself, and then you have the radiation and convection. And as I said, the convection plays the major role. So all that, I would say, all that, is given in the data sheet of the heatsink. That's the data sheet of the heatsink as a single resistance value, to which you add just the resistance of the interface between the component and the heatsink, and the resistance between the junction and the case of your component. This is given in the data sheet of component. And this is given in the data sheet of heatsink. As you've seen, this is all quite dependent on the size, the temperature, and also the orientation, which I forgot to tell. The orientation of heatsink is quite important as well, because this influences the convection efficiency. So the heatsink, I would say, it's quite straightforward to choose. The problem is how you do the cooling through the PCB, and a lot of times we do cooling through the PCB because it's just cheaper. So cooling through the PCB is done in two main ways. So the heat is transferred from this junction first to the case. This is the case, junction, case, also vertically, of course, but here it is also transferred through the leads, right? So when the heat is at the surface of your component, it is transferred vertically through the PCB, and mainly, really mainly, it is transferred through wires, because wires are made of copper, and copper is far better conductor than the rest of the PCB. When it is transferred vertically, it is also transferred horizontally through the PCB layers. But as you can see, these PCB layers are very thin, which means that the cross-section is much lower. Therefore, you need a larger width, let's say, of this conductor, which means you need a lot of area of copper. And then the heat is radiated and convected, I would say, through from these areas towards the surrounding. So what is important here to know is that your cooling area should be made of copper as much as possible. That's the first rule. And that copper vertically would be in forms of thermal wires, horizontally big copper planes. Of course, you may not be able to afford that. This is an example of the thermal pads. The components have sort of thermal pads on bottom, to which you actually solder them directly. So there is no air gap in between, which means that the heat is transferred through a continuous solid towards the thermal wires. And these are thermal wires here. And these thermal wires then conduct heat to the bottom layer, because as you see here, you cannot afford to have a continuous copper plane on top, because you have a component to be connected with the traces. So you cannot transfer the heat directly on top layer. You have to transfer it first to mid and bottom layers, and there you have to provide space or area of copper to be transferring heat horizontally. So that's the thermal pad idea on components. So if your component has a thermal pad, you have to use it. Use it as efficiently as possible using thermal wires and big copper planes. And how much do they actually transfer heat? What is their efficiency in transferring heat? This is shown here. In still air, the heat conductivity of 1 square centimeter of copper area, so the heat conductivity from copper area towards air, towards surrounding, is 1000 degrees of Celsius per watt per square centimeter, which means that if you are dissipating 1 watt of energy, of the power on a 1 square centimeter of copper, it will radiate or cause convection or conduction to the air at 1000 degrees change. In one direction it would, I will repeat that. If it would radiate and convect only on one side, then it would have 1000 degrees over the temperature of the ambient, which is a lot. Of course, you cannot force it, so you have to have at least, you usually have at least radiation in two directions, and then this would be halved. But nevertheless, that's a big number. So you cannot efficiently dissipate your heat away from the PCB just by a very, very small areas. You need something more. You need a bigger areas. And of course, if you can afford 100 square centimeters, then this figure would be much better. So the next question is, how is efficient the lateral conductions through the layers of the PCB? Through the copper, the value of this resistance, if you have 35 micrometer thick copper, the thickness, then that would be around 40 degrees of Celsius per watt, which means 1 watt of will be transferred at 40 degrees difference of temperature. Now FR4 is much worse. The FR4 is almost negligible. If you combine the FR4 of the thickness of 1.6 millimeters of FR4 and the copper is 35, it is still much worse. So conduction laterally, you should remember there, that is done primarily through copper layers, even though they are thinner. The cross conduction vertically is, let's say, because of FR4, mainly defined by the FR4 because it has much lower conduction than the copper. So if you have, even if you have copper covered over it, it doesn't help a lot because the FR4 has the main, I would say, defines the main property of conduction across the PCB. So the typical thickness is 1.5 millimeter, as you know, and that would range in 60 Celsius per watt. So if the difference of temperature is 60 Celsius, then you would get 1 watt of energy transferred through each square centimeter of your PCB. Now each wire you add, a typical thermal wire you add, is providing 100 degrees per watt. So that means that this 100 degrees per watt is connected parallel to 60 degrees per watt, which would get then a lower value. So adding, let's say, 10 wires would add 10 degrees per watt altogether because they are connected in parallel. So 100, like resistance, 100 ohms and 100 ohms 10 times would give you 10 ohms, right? And the same holds for thermal conductivity or thermal resistivity if you want. So the last thing is this heat conductivity to our surrounding. It depends on the orientation. So if your PCB is oriented vertically or horizontally, of your components, if they are on top or on bottom, that makes a big difference. Yeah, if your PCB is vertical, then this heat conductivity is lower. For a horizontal, if it's on top layer, it's similar, a little bit worse, but if it is on bottom layer, the components are less efficient cooled because the convection does not play a role as well as here or here, because the hot air is rising up. Of course, the airflow is improving things a lot, but you have to add some cooling fans. So let me show you an example how you can cool single component. For example, a linear voltage regulator, this one here. It's taken from the datasheet from the producer, and the links are given at the end of this presentation. Now this is a 3-pin device which has additional 4th pin, that one, which is mainly intended for cooling. So this is so-called cooling pad. And that one is primarily for cooling and nothing else. These 3 are electrically connected pins. That one is for heat transfer. So that one should be the one you should emphasize your design when you are thinking about cooling. So how do we calculate the power? First of all, you have to know what are the currents. And the currents into this 3-terminal regulator are defined or determined by the load current, of course, which you have to know. At least you can calculate or even measure it. Then there is a gate current, or the so-called quiescent current of this regulator. So this is the current which is consumed by the regulator itself, and those two are defining the input current. Okay, and then the power dissipation is this input current times this voltage difference, and this is this one here, plus the input voltage times this self-consumption current. And then by this knowing the power dissipation, you can calculate the required RTH junction ambient, which is a temperature difference, the junction maximum temperature, which is defined or determined by the manufacturer, and the maximum ambient temperature, which is determined by the user or the designer. So you have to define what would be your expected maximum ambient temperature. So this defines the temperature difference, and this is the Ohm law, which defines the maximum resistance between junction and ambient. Now, the data sheet will tell you, okay, the absolute maximum ratings are these here. And of course, this junction temperature should not ever be reached. The recommended operation conditions up to this value here. So this would be the maximum temperature. You should not increase or step over it for a longer time, I would say. Even you should keep under it in any circumstances. So this would be the maximum junction temperature you take, and probably you should go even less if you want longer lifetime. The thermal resistances are given here, and this is also an example showing you why this is the most important heat pad, or pad for cooling pad, sorry. Why? Because all the silicon die is actually sitting or glued to it. So this is in direct thermal contact to the silicon die, and the heat is primarily transferred through this pin here, this cooling pad. And now here you have to provide some copper area to cool even further. And this is the test sample that gives you these numbers I will show here. So all the other, here we have these 3 pins, right? And this is the case. Now here these pins are connected to the silicon die with a very thin bonding wires. And these bonding wires, of course, have very low heat conductivity, which means that they do not cool the component well. And here around you have some plastics, and this plastics is quite a good insulator as well, heat insulator. So the cooling towards this and this side is not very efficient. That one is. So you should take care of that primarily. So the thermal resistance between junction and ambient is a sum of thermal resistance of junction and case. Right? That one. And the thermal resistance of the case ambient. So the case ambient here is just the surrounding air of this component and this piece of copper here, and it is kept at 25 degrees. So in these conditions, you have these values here: junction ambient, junction case top, junction case bottom, and so on. So what they did, they made a PCB of different patterns. On top layer, this component is soldered, and starting with case number 1, you see that it has no additional copper layers or copper areas for cooling. There are smaller area, bigger, and the biggest here. And these all first 6 cases have no bottom copper at all. Then in case 7, they added a small bottom area around it, and then they kept the same top area till 11, and the bottom area was increased. And at the end, from case number 13 to 16, they increased the top area as well, and they increased bottom area with the same pattern as on top. So then they tested the temperature of this regulator, and here are the results. So these are the layouts for 1 to 16. These are the copper area sizes on top and bottom side, and these are thermal resistances, and I was interested in this one here, the 2 to 3 SOT case. So let us look at the first layout, number 1. This is the datasheet given thermal resistance, case ambient, which is measured according to this experiment. Now if we add a small number 2, a small area of copper just below it on top layer, it was decreased a little bit, but not much, because the size of this copper area is more or less the same as the case of the component. Now if we increase this to the number 6, when the top copper area is the biggest there is, you see number 6 has this value of 66, which means a lot of change. Now the temperature on top layer is dissipating very efficiently to the sides, and then it is radiating and convecting air into the surrounding ambient. So this is quite efficient. What about the bottom layer? In number 7 is the same as number 2, but it has additional bottom area, which then increases towards the number 11. So from 7 on, 123 would be comparable to that one. So adding some small bottom layer increases this as well. But at the end, number 11 has the larger bottom side area, but it is a little bit worse than if you had top area, because that makes sense. The heat has to travel through the PCB, which has some extra heat resistance. So this 11 case is worse than case number 6. But maybe you can afford larger area on bottom if you have a big round plane. On top layer, you may not be able to afford it because you have other components around. So let's go further. Now let's go to number 13. Now we have top and bottom layer of the same size, increasing towards number 16. So number 13 now is this one here, and the resistance is 93, which would be comparable maybe to a number, I don't know, 8 or 9 or something like that. But let's say number 13 is comparable to number 3 even. Let me see, number 13 has 93, number 3 has 84. Number 3 is even better. Number 3, this one here, is better than number 13, even though the number 13 has a bottom copper area. So going down to the larger, this is number 16, which has on top and bottom layer very similar structure than number 16 is this one here, similar to number 4, I would say. Has a thermal resistance of 70, while number 4 has 75. So I must say, according to this chart, the results, this graph would tell you the most. So increasing pad area is of course important, but it works best if it is increased on top layer. If you have half of that area on top and bottom, it's a little bit worse. If you have it only on bottom, it's of course the worst one among all. And the size of the area is very important. So having the very large area on top and of course also on bottom would be beneficial. And at the end, what you can do, well, you can afford maybe larger area on bottom because you may have a ground plane, while on top layer you have other components. So at the end, you need thermal wires. If you want to have efficient transfer of heat from top layer to bottom, you need thermal wires. And for that, you can then have a smaller top copper area and a bigger bottom. So okay, so thermal wires should be placed the most, let's say the most dense, just under the pad which has the most or the highest heat, which is the highest heat source, like this thermal pad, cooling pad on that component here. So here you put the most wires, but you don't put them around as close because you want that heat also to be transferred laterally. And I have a red pen and it can be seen here. So maybe I can just switch it. So now you see here the heat has to transfer only also linearly, laterally through these areas. And you don't want to put a lot of holes around it because the air inside these holes is not a good conductor. You need to provide or to leave space around so that the heat can transfer. But here it's the most important to be transferred to the bottom side, and here then it could then get transferred laterally as well on the bottom layer. So this is a way to go, and with large components you can afford to have pads, to have the thermal wires on the pad, because if you have thermal wires on a pad on a very small component, then you can get problems with soldering. But here it's not a big issue. Well, you can also have larger areas whenever you can, because even though you don't need them here at the input or here at the ground, you can still provide them. The larger the areas, the more the cooling. And I'm talking about areas of copper. What are the most common mistakes? Well, you can use thermal reliefs, which are good if you want to have a good soldering yield. But for thermal wires and thermal pads, don't use thermal reliefs, because what you did here, you get rid of all the advantages that copper can give you in thermal conductivity. So here, do not use thermal reliefs either around thermal wires or around thermal pads. And on bottom side, you may forget that this pin, cooling pin, is not necessary on ground. It could be on other potentials. Therefore, you have to provide this area on that potential. Don't just do like that, because these wires will not have any option or would be really deteriorated heat transfer laterally if they are not connected directly with copper. They are like isolated from the most conductive material here. So these, please do not do these mistakes. All right, what about other laminates? Well, we have also special laminates for high heat conductivity. For example, direct bonded copper, or IMS, the insulated metal substrate. In IMS, usually aluminum is used, and for the insulation between the copper tracks and the base material, which could be also copper, of course, is a very thin epoxy resin. While in the direct bonded copper, we usually have, of course, copper, and it is a ceramics that acts as an insulation layer between the tracks and the copper clad. Now, this copper has higher thermal conductivity than aluminum, but it's much expensive. So this is how the EMS or DBC looks like. We have a copper on top, we have a thin insulation layer, and we have a big copper clad in the bottom. And this would then provide a really good thermal conductivity towards the, let's say, heatsink. But people still, most of the time, if it is possible, don't use these laminates because they are expensive. And yeah, they rather do a lot of different tricks with these thermal wires and copper areas and stuff like that, instead of using metal laminates. Because in metal laminates, you're also quite limited with number of layers. Well, the most usually you have only one, which of course may be a big disadvantage. So for the end, I will give you a simple example from one of my master students, or actually it was diploma student, which was working or still works who is working in Gila Saturnus on the LED light sources. And here he did an experiment with different laminates for the LED diodes. This is his design. These are two LED diodes that he powers with this big ground and power planes. And he used different number of thermal wires and different materials for the laminate. So what he used FR4 without wires, or FR4 with one wire, 5 or 12 wires, and then he also used aluminum IMS. He didn't use copper, direct bonded copper, because that would be the most expensive material. He did not want to even try, because in automotive industry, you all know how they are trying to get the cost down. All right, so you see that adding a single wire, metallized wire, would increase the price of the PCB a lot, because that, well, not that a lot, but still, because a single wire means another metallization process. But then if you add 5 or 12 or whatever wires, it doesn't change much. The aluminum IMS, on the other hand, is much expensive. So that's the reason why they are trying to keep within the standard FR4 material. So he did this design, and he put a lot of thermocouple sensors to different points on the circuit. He actually glued them with a special glue. So here he put 4 sensors on the same side around this diode, being sensor number 4 the closest to the LED, and then sensor number 6 the closest to the other LED. So then on bottom side he had, again, he put 4 sensors just below these 4 here to measure the temperature on the back side, and sensor number 10 was again just below the LED. Why did he do that in that way? Because he wanted to measure on back and front side and he also wanted to compare the temperature of the other LED. If these sensors would affect the heat transfer, he would detect it by that. So these are the results. So he just check, please, number 4 and number 10. The number 4 is the LED in front. The number 10 is just at the back of the LED. And you see the big difference if you use FR4 without wires or even with 12 wires. You see that the temperature changes maybe for 5 or even less degrees. So with 12 wires, the temperature of LED is 5 degrees or similarly lower. And on the back side, of course, it increases because then it has to dissipate laterally. So the wires does help decreasing the temperature of the LED by some amount. And of course, since the heat is transferred to the backside, the temperature at the backside increases. The TP6 and TP4 are quite close, so it seems that the sensors do not affect much. But now the CM3 seems to be a little bit better. The CM3 material without wires seems to work a little bit better than the FR4, but not significantly, I must say, because the most effect you get is aluminum IMS. The aluminum IMS, again, you see how it affects the temperature of the LED really severely. Now you see that the temperature difference between front and back side is only around 5 degrees, while here it is around, the temperature difference is around 20, and here around 30. So the FR4 without wires, the temperature difference between back and forth sides is around 30 degrees. With 12 wires, it is around 20. And if aluminum IMS is taken, then the temperature difference is just 5 degrees between front and back side. Now if we go and look at the thermal image, you see that here with wires or without wires, well, doesn't make a big change. The thing is that, of course, the lateral transfer of heat is not affected by these wires a lot. What they do is just they transfer heat to the backside. But at the backside, actually, the board was faced towards the desk, the table. So it actually did not, the heat transfer to the backside did not help a lot. The big difference was when we used the IMS, because here you see that already in 1 minute the temperature was quite spread on the whole PCB, and it was more or less in the same range. So this is the scale. So you see now that by using aluminum IMS or even DBC in that sense, it really helps a lot when dissipating power and the cooling of the components. As you see, the heat spreads around the whole PCB very quickly, while in the case of FR4, not really. He also used some simulations. He did simulations in 3 different softwares with different accuracies. And these simulation softwares, I must say, they differ mainly in the material libraries and component libraries, because the hardest part is to define all the thermal properties of all components. And if you have a really good library, then you can simulate quickly. Otherwise, you have to really define every single piece manually, which takes a lot of time. So his simulations using 3 different software packages shown that were quite close to the results here, in the range of few degrees, except one software which was having a little bit more trouble here. And these are the measurement results. The violet one are the measurement results, which were quite okay at this point of the LEDs, but not that good away from them. I'm talking about difference more than 5 degrees. So the difference in temperature was here more than 5 degrees, around 7 or so. While here it was a little bit closer. So I must say that the temperature or the heat transfer modeling was okay, close to the source, and it was getting worse and worse, going away from the source. So the properties of the PCB may not be so well defined. And even if you take the PCB without wires or with wires, it did not help a lot regarding the accuracy. Now at the end, these are the measurements on the IMS when the accuracy was a little bit better, since I suppose the IMS material was defined with better material properties, where the results were actually in range of, I would say, 2 degrees Celsius or plus minus 1 degree Celsius, when actually is a very, very good result. So for the end, I just wanted to show you how the things are done in industry and how close they can come to the final value. So after this lecture, you should be able to explain all 3 physical heat transfer mechanisms and their basics modeling approach. You should rank some materials for their thermal properties, such as that you know about the solids, liquids, and gases, and what about the conductivity, electrical and thermal conductivity relation. Then you should be able to construct an equivalent circuit for a simple thermal case, thermal task, thermal or cooling task. So you should be able to construct some circuit with resistances, equivalent electrical circuit with electrical resistances that would then be used for simulating the heat transfer, and then calculate a simple heat transfer problem. You should be able to determine the heatsink parameters for a given problem and choose appropriate material for a PCB design, and especially be able to design a PCB for a passive cooling of a component through the PCB, so that you can design properly the copper areas and the thermal wires. And here is some literature, for example, some of the application notes regarding cooling of components. And here are the last 3 links that are linked or that are defining or determining and showing the cooling of the LM1117, which I showed before as an example. So what can I tell you for the end of this semester and this lecture in particular? Well, cooling of components, it's a quite demanding task if you are at the limit. So that means that you are on a very, determined and confined space, that you have a lot of heat sources, that you have quite limited means of cooling, and that you are very limited with the budget. So in that case, you really have to go to the edge. And in case of, let's say, LED front lamps for cars, they actually have to calculate up to a degrees of Celsius accuracy, and they are always working at the limit of the temperatures of the LED diodes. So this is an example of a quite extreme one for an industry that I know. Now, if you're working with a simple electronics that does not dissipate a lot of heat, then you may not be even bothered at all. So what I would require from you is not to calculate the sizes of the copper areas which you have to add, but when you have a design which has a, let's say, a requirement for cooling, you should be able at least to use the basic principles that for that design. For example, that you add some copper area, that you don't use thermal reliefs, that you add thermal wires, and you connect the bottom copper to it as well. So about the size, of course, I cannot ask you to calculate and to determine the correct size of that areas. Of course, that is completely different story. As you've seen, it's more rule of thumb calculation. For all the most, how to say, more accurate calculations, you have to use some simulation software for that matter. And what can I say at the end of this subject as a whole? Well, we covered quite a lot of different areas, different aspects of PCB design. We did not cover a lot of them as well because there is just not enough time. And I must say it's quite overwhelming altogether, I must admit. It's quite, I would say, big area and quite demanding as well for example, even, I mean, especially for those who are less familiar with the subject. I'm aware of that, and I want to make it as easy for you as possible to get the grasp to this vast area, to this field, and to get some expertise as well, that you may be able to use them when you are doing this kind of work in your professional life.